Hi class, welcome back. Today we're going to discuss once again the area under the region, but in this section is going to be a little more specific. It's going to be the area of the region between two curves. So the objectives are to sort of bring back the concept of the area of the region, but then extend it to a different case. This will allow us to actually find the area between two curves, and therefore it's going to open, we can use this as a tool to open more possibilities of specific areas that we want to find. So the objectives are to find the region between two curves using integration, find the area of a region between intersecting curves using integration, then describe the integration as an accumulation process. So the main concept here, it's actually not so different than the way we described it earlier. There's only like a small twist. So let me just sort of kind of give you a quick recap of how we define the area on the curve. So here we have the function right there, and we have specific values of x that we were bounding, that we bounded this region. Let me put this in a different color. Now I want to point out that this region is specifically above the x-axis, right? So this region is what the area that we're looking for. Well, we know that to find the area under this curve and above this x-axis, it was always defined to be just simply the definite integral from a to b of f of x dx. Now we could extend this, and we can connect this to the new concept by arguing that, hey, there's like an imaginary minus 0 going on here, as I pointed out on the next line, thus stating that the possibility that this area is actually the area between two functions, this function f and this function x y equals 0. So this is y equals 0. And so what we are sort of arguing here in this case is that you can actually find the area between two curves, this curve and this curve, by subtracting the two curves and then taking the definite integral. And so if you guys think about over here, as we extend the concept and we want to find the area between these two curves bounded by a and b, then we can say, well, it's sort of kind of like the idea that, hey, we can find the area of f, right, between a and b would be all this, right? It will be all this, and then we come back and you subtract this part, right? This area, the area of g below the below g, right? So if you have this whole thing and then you take away this, then what's left behind? This part right here, right? So that sort of kind of extends the concept, right? It says it's sort of it's consistent with what we had before, because you can see here you have the function on top minus the function on the bottom, take the difference of those two and then take the definite integral, and that will actually give us the area between the curves. So that's not actually not so different than what we've done before, right? It's sort of, we were sort of doing that for a g equals 0, right? And that's pretty much it, right? That's the main thing we want to get from this section. Obviously we're going to extend this further, but that is the main concept. So the area of a region between two curves is going to be, assuming the f and g are continuous on between a and b, and it's very important for us to know that g is always less than or equal to f of x, right, in between a and b. So what we're saying is that we want to make sure that f stays to be lower, right? It's important to keep the order correctly. You should always have the top function minus the bottom function. Otherwise, what algebraically would happen is that you will end up getting the negative value of it. Anyway, so that's important for us to recognize that G is lower than F for all values of A and B. Now it could happen that they change, right? But we don't care what happens over here because all we're doing is finding the area between A and B, right? So they could change as long as they stay this way between A and B. All right, and that's it, right? That's all we have to do. We just have to set up this integral here. And that's the concept follows the same idea that we're sort of making infinite rectangles, right? The height of this the height of this rectangle is described by the difference between F and G. That gives you the height of it. You already know how to get the width. That will be equal to delta x. So it just follows the same concept as before, right? It's very consistent. So let's try an example here. So they're asking us to find the area between the two regions. Find the area of the region bounded by the graph f and the graph g, which is negative x, and bounded by the boundaries x equals 0 and x equals 1. So I have here a picture of it. So here we have f, here we have g, and then we're restricting this region on the left side by x equals 0, right? X equals 0 and x equals 1. So it's clearly what the region is. Now, the idea at the end is that we should be able to find this area and set up the problem without actually looking at a picture, right? Here it's kind of nice, right? Because I can see the picture, I can see which one is the top function, and I can see which one's the bottom function. But actually, we don't even need to know that. I mean, we can figure out which one is the top function, which one's the bottom function, by looking at the structure of the function, and sort of making a rough draft idea in your mind. Sometimes it will require for us to actually graph it, as you guys will see in a few examples that we'll have later. All right, so for now, let's just focus on the picture, one step at a time, right? Let's get used to this concept of just finding the area between two curves first, and then we'll get into more hands-on techniques that we can find whether G and F are greater or are less than each other by doing some algebra. Okay, so all right, so obviously G is less than F, so that means that you're gonna have the top function minus the bottom function, right? So think about this is top minus bottom, right? And then you're gonna simplify that before you integrate. You already know how to integrate. You know how to set up those two. That goes from 0 to 1. F is x squared plus 2 minus, right? It's very important. It's minus and then parentheses whatever G is. Now G happens to be one term, but obviously you guys know what would happen if there's multiple terms. You're gonna make sure that negative is distributed, right? So parentheses is very important for you guys to keep note. All right, so we'll simplify that by just doing simple algebra, right? And then we'll integrate this. Simple integration by using power rule give us x cubed over 3 plus x squared over 2 plus 2x. And then evaluate from 0 to 1. And then we'll plug it in, right? Plug in first 1, 1, 1, 1. That's how we got that one. Minus big parentheses. Now plug in 0, 0, 0, 0, right? I'll let you guys follow that algebra there. And so now we have those two. This becomes 0, obviously. So all we have to do is simplify this number. Then you have to find common denominator, which is 6. And then this will give us 17 over 6, right? The details of the algebra, I'm sure you guys can follow that. Finding common denominator. Anyways, so basically the concept here is the new concept is that you have the top function minus the bottom function. That's the new thing, right? And obviously that will give us the area between the curve. So that's it, right? That's the main thing that we're trying to understand now. All right. Obviously we'll do a few more things, but we'll figure out like how to do extended techniques that will help us set up the problem. All right, so like in the next example. On the next example is asking us to find the area of the region between the intersecting curves. So if you guys notice, when they tell you the word intersecting, that's going to be a clue to tell you that they won't give you the boundaries A and B. They won't. Instead, to find the boundaries A and B, you will find them by looking at the place where the two curves intersect. So that means what they're saying here is that they want us to find the area between the two curves in the intersection of the two curves, right? So here, if you notice, this is your parabola facing down, this is your linear, but if you notice that this is the only region where it's between each other and between the two intersections, right? So here is the place where the function is intersecting, and here's the other place where the function is intersecting. So what this language is saying that they want us to find specifically this region, right? Now we don't know what that value is, and we don't know what that value is. I mean, we can see that that's going to be a -2, and that's going to be a 1. Now, obviously, because we graph the picture, right? A lot of times, again, you don't have we're not given that, so you have to come up with it. And obviously, even if you graph it with your calculator, you'll be guessing what those values are. Sometimes those could be decimals, so you're not certain what numbers would those be without eyeballing it, right? By looking at the picture. So we can do this in an alternative way, and that's what I expect you guys to be able to do. It is some basic algebra step, so we know how to do this from previous courses. I know if this is maybe that you might have to try this on your own a few times to remember and review, so go ahead and do that. All right, so let's go ahead and try the problem. So a region lying between two intersecting graphs. Find the area region bounded by the two functions. Now, you should be able to do this in your head, right? You should already think about that this is a parabola, right? We spend so much time in college algebra learning about these functions, and this is the benefit of it, right? We sort of now have a better understanding how these functions look like without actually even graphing them. We know that this function is facing down, has a parabola facing down, is shifted 2 units up. We know this is a line with the intercept at x equals 0, right? So you should know that, right? We should have a better understanding of that. All right, so also, since we are not given A and B, right, we gotta find what are gonna be the boundaries, right? What's gonna be the end of the graph, right? That tells you how far to the left you're gonna be going, and how far to the right you're gonna be going. That will tell you what A will be, and this will tell you what B would be, right? We need to know those because those will go here. So anyways, how do we find this? It's actually very direct, right? The concept is we know that these two graphs are equal to each other there, right? They're intersecting, so therefore this value is equal to that value. So therefore we're gonna solve for x whenever those two are equal to each other, and that's what we're gonna do. We're gonna set them equal to each other and then solve for x. As simple as that, right? What we're gonna do, we're gonna move everything, we're gonna subtract x on both sides. That's how we got this. We can factor a -1 first, and then what we're gonna do, we're gonna factor this out, and that gives us this, right? And then we can solve for each of the factors, and that gives us this, right? X equals -2, x equals 1. So those are your A and B's, right? Those are your A and B's. That's your A, always is the smallest one, B is always the biggest one, right? And then we also know that between those two numbers, by looking at the picture, right, we can figure out that G is lower than F, right? Now again, I'll show you guys how we can do this without looking at the picture in a second, but let me just focus on the setup. Let's do the integral, and I'll come back and talk about that in a second. All right, so we're gonna set up the problem because there are two curves. We're gonna say it's gonna be from A to B, f of x minus g of x. Again, it's always top minus bottom, right? And so we did that, right? It'll be from -2 to 1. F of x is the top, x is the bottom. and then you simplify that. Don't forget the minus and don't forget the parentheses. Then you simplify it, and then you once you do the integral, then you set up plugging 1 and -2, and that's how we got those two numbers. And then all this is just algebra, and I wrote a detail value here. You have to simplify. You add these together, and then this together, right? And that's how we got those two. And add these, give you that, add that, gives you that, and add that, gives you that. And that simplifies to be a -3. That simplifies, that's a 6, and that's 3/2, and then find common denominator, and that gives 9/2. All right, so we know we can do that, right? That's not the issue. So one way that we can figure out that f of x is the top one and g of x is the bottom one is simply by plugging a number, any number that is between -2 and 1, between -1 and -2 and 1, right? So once you figure out these numbers, you can literally just plug in any number between here and here into there and into there. By plugging that number, that will tell you which one is greater. For example, plug in the easiest number that you can, x equals 0. So if you plug in x equals 0 here, what do you get? 0, right? Okay, well, what about this one? What about if you plug in x equals 0 there? What do you get? 2 minus 0 squared. That gives you 2. So this is higher than this, right? So therefore, that's how you got the 2 there. That's how you got the 0 there, right? So it's very, very simple, right? Just plug in a number between -2 and 1. To now overthink that problem, it's a nice technique that we can do. And then here I have a few practice problems. I actually will try a few of those after this video. I'm sort of sticking here to the overview, and I'll try some of these practice problems next. All right, so good. We know how to find the area between two curves. We know how to find the area even if they don't give us the boundaries by the intersecting curves. And then, but here we're going to describe an alternative way where we can actually find a well, the way we can kind of see this area. So one way we can think about this is by thinking that basically what we're doing is we're trying to do the height times the width, right? And so the area of this will be the height times the width. We can figure out the height by taking the difference of the two functions. That will give us the height of the rectangle, and then multiply by the width. And that's sort of how that comes out, right? So in the next example, we're going to find the area of the region bounded by the graph, right? And the x-axis, right? Describe the integration as an accumulation process. So so here they're giving us the problem, right? We already have the problem here of the picture. They want us to find this area right there between this curve and this curve, right? So basically the g function, here's your f function, and then here your g function is 0, right? So therefore you have f of x minus 0 is just going to be that, right? And we're going from -2 to 2. So the way I want you guys to start thinking about this is sort of the idea of a accumulation of area. If you think about it, it's like what you're doing is you're adding, you're finding the area of one rectangle, right? Finding the area of one rectangle, and then sweeping this around, right? You're sweeping this around for your delta x, right? So by doing that, you're sort of, if you think about it, from here you have 0 area, from -2 to 2, because there's no accumulation of area. Here, as long as you start sweeping around from -2 to -1, you accumulate some area. If you continue with that sweeping, you accumulate more area, right? And then if you continue with this, you sort of continue with accumulating more area and accumulating more area. So anyways, so this concept of a sweeping here, it's going to be very relevant later on in the next section when we start talking about volumes. So it's actually kind of neat, right? If you want to find the area of a region, find the height of it, and then do this sweep around, right? This sweep around tends to be your delta x or your dx, right? All right. So there's another example that I want to talk about, and that is specifically practice number 5. And in this example, this will give us an extension concept of how to find the area under a curve whenever in respect to a different variable, and instead of x, do it instead of a y, which means this is sort of known as the horizontal representation rectangle. And I'll talk about that in the next section, in the next video.